the number of disk accesses you have to do. And n is this number of items in the dictionary that you're talking about. So the dictionary is what the data structures people call, something like an index. And B is the size of the block. And then fractal trees are going to be much better, as we'll see. So just to sort of just warm up. Okay, so B trees look like this. There's a tree. Well, let's start with just binary trees. I think that's better. So a binary tree is a search tree. And if you put things into it, like 1, 3, 5, 8, 12, 14, the property of a search tree is that everything on the left side is less than everything on the right side. And what that gives you that's different from, say, a hash table is that, see, hash tables can do put and get just fine, but what can a tree do that hash tables can't do? Next, right? It can tell you the next item. So there's a 5. What's the next one? And that's the reason why we have to pay that log factor instead of what a hash table is, which is constant time to do any kind of operation. So the way you do a B tree is, well, first of all, what's the depth of this tree? If we just were to lay this out on a disk and not worry about layout. So each of these nodes of the tree is placed randomly on a disk. It's a data structure. So how many disk IOs do we have to do in order to do a lookup in the worst case? If it's a nice, uniform, balanced binary tree.
Is it B plus tree or B tree?
This is a binary tree.
Okay, so
everything that's interesting is that
all the stuff.
And we're talking about the worst case cost, which means that it doesn't matter whether it's a B plus tree or a B star tree or what. Because in the worst case you have to go down to the leaf. Right? So I'm generally doing B plus trees because it turns out that it's silly to actually keep data near the root of these trees because that's. So the answer to this is that the depth of this tree is log base 2 of n. Right? That's how deep a binary tree is. And so if you think of n as being a trillion, whenever I write log, I'm going to just sort of mean log base 2 because I'm a computer scientist, not a natural scientist. I'm not going to use the natural log. So if n were a trillion, n is 2 to the 40th, then that would be like 40 disk IOs in the worst case. And that would be 40 disk IOs at 100 per second. It's sort of like half a second to seek down the tree in the worst case. So that's why binary trees aren't used to implement indexes in databases. And so what you do is you say, well, I've got a block size on my disk. As long as I've done a seek, I might as well fetch more than one bit off the disk. And so I'm going to group this up together into blocks. And here the block size is sort of 4, so I can have a fan out of 4 from this block. And if I so the only difference between a B tree and a binary tree then is the layout. Is that I've laid out the binary tree so that this first few levels of the tree are all together on one block, and I have a fan out of B effectively inside that block. And so that changes my performance for the depth of this tree, counting the number of disk IOs, because that's all we really care about in this model, to log base B of n. Does that make sense? Because this is the height of this thing is log B, and so that's a log B. So the height of this thing, the other way to express that is that that's log n divided by log B. And here, so you have a fan, there's two ways to think of this. You have a fan out of B, so the depth of the tree is log base B, or you have a tree where which is composed of these things where for a single disk IO you get to do log B work, and you have to do a total of log n work, so you do log n divided by log B. So there's two different ways of measuring the number of disk IOs. And that comes out to be much better, because if B is, I don't know, for NODB, B is, see, the number B here isn't really the block size, it's the number of items in the block when you're doing this kind of analysis. So now I have to do an assumption. Let's say that the items are 100 byte objects in the tree. And NODB uses 16 kilobyte blocks, so that means you can sort of have 160 objects in a node. That seems like a reasonable assumption. We could do a different assumption. It doesn't really matter.
Yeah.
So let's say 256, because that's a power of 2. So you would have the log base n is 40, and the log of b, which is 256, is 8. So that means that if you had an InnoBase data structure with sort of order 100 bytes for a key, and there were 1 trillion items in it, you would have to do 5 disk IOs in the worst case. Which is, that worst case probably isn't happening very often, right? Because the root of the tree is being cached in main memory. And probably all the children of the root are being cached in main memory. And most databases that I've seen configured, people end up configuring it so that everything up to the bottom level, the main memory is big enough to hold everything except possibly the final layer of the tree. So that means that in practice, most people configure their B trees so that it costs 1 disk IO in the worst case to do a search, right? But let's be theoretical and talk about. So this is where this number comes from. That's log base B of n, which is the same as order log n divided by log b.
I will argue because InnoDB has the record also in the last one. That means that it will be, for trillion items, probably do 2 disk seeks, not 1.
Pardon?
It will probably do 2 disk seeks, not 1, because it also keeps the row in the last in the last level. So that actually in a trillion item, it can't keep the 2 lowest level in the memory.
Well, it depends how much main memory you have, but
But assuming it's
1 or 2, you know, whatever. If I abstract, so this is a worst case situation, which isn't going to reflect people's experience in practice, because this is completely cold cache, and now I'm going to do a lookup, and the number of lookups, and there's a big O here, so who knows what constants may actually be hidden inside there, okay, so that's B trees. So now we're warmed up. We've got a little bit of common language between this. We can talk about, what happens with fractal trees. So I'll go ahead and write the number up here. The performance of a fractal tree is big O of log B log n. It's a funny reason. Over B. So that's a lot bigger number. So if I actually work out what log n is 40, and B was, for the case that we talked about, was like 256. So that's less than 1. And so to say that it's a little strange, because this is the average cost of an insertion in the worst case. So some insertions, clearly you have to do a disk IO, but on average you don't have to. If you do a whole bunch of insertions, in the worst case insertion pattern, it's that much per insertion, which is, so that, what is that, 1/6 of a disk IO. Now, in practice, what happens is, for the data structures that we're using, because the block size we can make a lot bigger, we do, and we make the block size be on the order of 4 megabytes. So 4 megabytes divided by 400 would be like 40,000. So we're talking about 1,000th of a disk IO per insertion. So the rest of this talk is basically going to be to explain to you how you can get search costs that are like that, and have the insertion, I'm sorry, that was insertion, that's the insertion cost. This is so bad for me to have done this wrong. Search cost is the same, because there's a lower bound argument for that. I apologize. Search cost is order log base B of n. And for fractal trees, it's also order log base B of n. And there's a lower bound argument that says for doing a lookup for a tree data structure, that's what it's going to cost you in the worst case. And it has to do it's a counting argument. The old argument is that says, well, if I have n objects and I have a tree with degree b, there's going to be some path that's at least log base b of n. And so that's the search cost, hasn't changed. So how can I get the insertion cost down by this factor of 1,000? It's really more like a factor of 200, and get without hurting the search cost. So the first step is to realize that although there's a lower bound argument for the search that I've given you, the lower bound argument for insertion that argument doesn't work for insertion. So if I have a data structure that can do put and get and next, those are the three operations, right? Well, if I want to make insertion fast, how can I do it? Well, if I don't care how fast, the hint is, if I don't care how fast get and next are, how can I make insertion fast? Append, right? Just right to the end of a file or an array or something. Mm-hmm. So what's the average cost of an insertion for the append type data?
O1?
It's better than O1. This average cost in terms of number of disk IOs.
No, 0, because you know where it is.
It's not
already.
0. You have to do some disk IOs.
For the write itself.
It's divided by amount of records you're inserting.
It's order for append. So I'll go ahead and make a row here. I'll just stand this table sideways. I didn't plan ahead. So the append data structure, we had insert. It's order 1 over b, because every b items I actually have to do the write. So I get to insert b items, and then there's a disk IO eventually for that block. I insert b more items. So that if b is 1 in 40,000, this explains essentially why that data structure can do append at disk bandwidth, because that's what it's doing. The lookup cost for that data structure is order what? How long does it take to do a lookup if you don't have a tree?
And divided by 2?
Well, the worst case,
Well, worst case is n.
but even if it were divided by 2, I get to hide that in the big O, so n over 2, whatever you like. However, it's not n, right? Remember, how many disk IOs? N over b, because every time I do a disk IO, I get b items. So I can, if all you're caring about is the number of disk IOs, it's n over b. So we've got this, which is much better than this, or even this, and we've got this performance, which is much, much better than that. And so the challenge is, I'll show you how to build a data structure that gets not quite that much performance, right? There's a log n worse than the performance you get out of the append, but certainly nothing like this bad. Be about the same as a B tree.
Okay, but actually, wasn't at the beginning, I missed a couple of minutes. But you assume you know a B tree star, I assume, that has actually the data as part of the B tree. But while, for example, my ISAM has the data in append mode. So only the indexes are in B tree, all the data is in append. So we get exactly the same thing as the fractal tree.
No, because if the index doesn't fit in main memory, then you have to do disk IOs to do the insertions.
Not for the data. And we don't need indexes. We can also do it without indexes.
So if you're not having a B tree,
I mean, the thing is that
if you don't have a B tree, so you have a MyISM data structure with
Yeah.
no index, then that's not what we're talking about here. We're talking about data structures with indexes.
Yeah, but I mean, the also thing is that you have, you get the same benefit of with append for the data itself, if you have the data outside. And
So yes,
yeah.
perhaps so. But if you're going to maintain the indexes, you have the problem of maintaining the indexes, and in which case you're facing this, this kind of trade-off that you actually have to do some disk IOs as the index gets bigger than main memory. If you don't have indexes, then you face this cost that it's going to cost you something to find something.
except that the indexes are much smaller because you don't have the data as part of the B tree.
The indexes, we're talking asymptotics here. So we're talking about the question of what is the worst case behavior, and if you have an index where your indexes fit in main memory, then you're not going to see some of these effects, because that's a small index by the standards of my customers.
Yeah.
So we're talking about, from a practical, putting on our practical hat here instead of the theory hat, Talking about cases where the indexes are bigger than main memory by more than a factor of 2.
Okay.
Okay? And if you have a small data structure that fits in main memory, then there's lots of good things you can do. And it's not, you shouldn't be using a B tree in that case anyway. A binary tree would be a better choice.
Actually, I think there's proven that even in memory, B trees are better than binary trees because of CPU caches. But that's a different topic.
Well, they're block size, because of CPU cache misses, the B for the B tree is the cache size line, which is maybe 64 bytes or something. So yes, if you want to minimize the number of CPU cache misses, you build a B tree that's tuned for a block size of 64 bytes, which for small keys you can actually get a fan out of 4 or something. But if you have the case where if you have a case where a key is big O of a cache line.
Actually, it's even faster than that. I think somebody proved that up to 256 bytes, it's still faster than B trees.
Well, you get some effects, things like TLB misses and so forth.
Yeah.
However,
However,
and this is Michael Stoneberger's argument, is that if you can get your database to fit in main memory, and this is what VaultDB is all about, if you can get your database to fit in main memory, then you might as well just use a binary tree. Because the difference in performance between a binary tree and a 3-area or 4-area tree, and it doesn't make sense to try to get up to like 6-area or something, that's a funny thing, is, you're talking about thousands and thousands of insertions per second in the worst case, transactions per second in all the cases. So that's his game. Okay, so now I'm going to tell you how to implement a fractal tree that can get these kinds of asymptotic bounds. I haven't even told you how big main memory is. Main memory is not in this picture. This is the number of cache misses in the worst case, assuming a fairly small main memory. And clearly, as you have more and more main memory, the applicability of B trees becomes wider because you can fit more stuff into main memory and it doesn't cost you as much to do the insertions and so forth. Okay, so I'm going to show you a fractal tree implementation. It's a data structure. It's not the one we actually use in our storage engine, but it achieves these things, and it's got some shortcomings, which is why we don't use it. But it's something that's simple enough that I can explain it in sort of the time frame that we have. So here's the data structure. I'm going to have a collection of arrays. That's a funny number. I want to have powers of 2 here. So this one is size 1 and size 2 and size 4 and size 8 and 16 and so forth. So that's the first thing, is there's arrays of size, there's one array of size 2 to the I for every integer I. Can I write larger? I can try. That's the first property. The second property is that each array is either full or empty at any point during the operation of the data structure. So this data structure, if I have one item in it, there's only one place I can put that one item. It's going to be right here, because that's the only, if I put it here, then the array is not full. If I have 2 items, it has to go here. They both have to go here. If I have 3 items, well, 2 of them have to go here and 1 have here. And essentially, if I take the binary representation of the number of items, that tells me which arrays it has to be in. So if I have 5, I have to fill in this array and put 1 item there. Okay? And then the third invariant is that each array is sorted. So there's no relationship, so if I put in some numbers here, I'll have like 1 and 3 and 8 and 12. Those have to be increasing order. If I had a 7 here, it doesn't have to have any sort order with respect to this one. So I could put a 0 up here or a 13. I could take any one of these items and swap it out with this and insert the 7 in the right place. And that would be a valid data structure by these 3 rules. Clear so far? Okay. So now how do let's examine how to do a lookup in this data structure. Any ideas? I want to look up something. I have these up to log n sorted arrays. Yeah.
Start from the top.
Start at the top. then,
you can. It's not gonna
so
work right. That's
I'm
not
looking
right.
up, 9, right? So I look, it's not here.
You jump into the middle of each.
Yeah, jump in the middle of
I
each.
do a binary search on each array, right?
Mhm.
And I don't need a tree or anything. I can do a binary search. So that's going to cost me log base n, well, log base 4. It's going to cost me log 4 disk IOs to do a binary search, because this has the same problem that a binary tree has, is that it's not log base b of 4, it's log base 2 of 4, because I actually end up possibly doing a disk IO for every item. So it's log of 4 plus log of 1, and if there was something here, I'd have to pay log of 2, and if there was something here, I'd have to pay log of 8, and so forth, until I got up to log of n, whatever n is. So the cost of that lookup, total cost, is the sum of all these. Right? How does this one relate to this one? It's one more, right? This is 1. This is 2. Actually, that's 0, but that's 1. That's 2. That's 3. Until we get up to log of n. So it's an arithmetic sequence. I'm summing up the numbers from 1 to log n. The previous one was log of n minus 1, and so forth. So that adds up to this data. I'll keep appending here. So this is called a cache oblivious look ahead array, and so the insert and then the lookup. So far, the lookup cost is log squared n. And there's a big O here.
I was wondering if it was true that you wanted to look at the biggest one first because it was more likely to be there, or whether.
Well, let's do a worst case analysis. Instead of
Sure.
what
Okay.
you're talking about is a heuristic that might improve the best case or might not. And we can,
That's fine.
let's do
Okay.
worst case analysis. So the worst case is I'm gonna have to look at them all. I'm looking up something that's not
It's
there
in
at
the
all.
last one. Oh, it's not there.
It's not even there, so I have to look at them all to find that out. And so that's log squared of n, which is a lot worse than log base b of n, because it's not base b for one thing. So there's that difference between 5 and 40. So that's 40 squared. So that's 1,600 disk IOs for that case that we were talking about. So now we're talking about 16 seconds worth of disk IOs to do a lookup for this data structure.
Why is it a log square?
Because the cost of looking up in the last array is log n,
Yeah.
and the one array before that is 1 less than log n. So if the last array was,
But that's 1 plus 2 plus 3 plus 4.
So it's-
But that's not the same thing as log square.
the last number is log n.
Yeah.
So the sum of the numbers from I equals 0
Yeah.
to log n of I is big O of log squared n. It's actually log of n times log of n minus 1 divided by 2, but
Yeah, I was gonna say, it's n times n minus 1 over 2.
it's this
where
times
n
this
is log
minus-
n.
Yeah, well, yeah.
Which is roughly equivalent to log squared.
It's
a little bit.
big O equivalent. It's a
Yeah,
factor of
okay.
2 off,
Yeah.
and
Yeah.
we're doing big O's
Okay.
here, so I can ignore factors of 2.
Okay.
Okay? So yeah, there's a factor of 2 advantage, and plus it's not exactly log squared, it's log of n times 1 less than log of n divided by 2, but that's
Yeah.
big O of log squared n. So far I haven't delivered on my promise of showing you how to do the fast insertions, but asymptotically, at least this is faster than this, so at least I'm going to come up with, the first thing I'm going to do is come up with a point that's somewhere between here and here. It's going to be nearly as good. It's going to be fast at insertions. It's going to be a lot worse at lookups. Then I'll show you how to make the lookups fast. Okay? So,
Oh, sorry. I was going to ask what colo stood for again.
cache oblivious look ahead array.
Okay, thanks.
So far, the array part of this name I've explained to you. It's a collection of log n arrays. I could go ahead and tell you some part of the other name. The cache oblivious part is A data structure like a B tree is cache aware. It has to know the block size, right? So the block size is encoded into that data structure. Nowhere in this data structure do you see the block size encoded, right? I just have this array, and this array, and this array, and this array, and I just lay them out in linear order on the disk. And I haven't coded up the block size. So the data structure doesn't care what the block size is. If I move this from one disk system to another that's got different ratios of bandwidth and different native block sizes, the data structure is the same data structure. All right? So this is cache oblivious in that it doesn't know what the block size is. The surprising theoretical result is that there exist optimal, asymptotically optimal, cache oblivious algorithms for a bunch of problems like FFT and matrix multiplication and B-tree implementation and priority queues and a whole bunch of things. String B-trees, and there's a whole bunch of academic researchers who've gone off and found cache oblivious data structures, which when you map them onto a cache hierarchy where you don't know the block size, they still provide optimal performance. Yeah?
Can I claim to be clever about the layout of these arrays so I can binary search across all of them, even though some may be empty, and then it's log2n to search?
Well, okay, so let's go ahead and get rid of one of the logs. Right? Here's how you get rid of one of the logs. And then I'll show you how to get rid of the log and turn it into a log-based B. So getting rid of one of the logs is having done a binary search up to this point. I have some clue that in principle, I have some clue about where the item is in the next array. If I knew where 3 and 8 were in the next array, I'll put a little pointer in there, then I can restrict the scope of my search on the next array to between here and here, right? So if I can, by a little bit of trickery, make it so that these two pointers are only a constant distance apart, then I can get rid of a log factor, because basically I'm doing log n lookups, but each one is only looking at a constant number of items. This is a trick due to Richard Cole called cascading data structure. And so the first part of the trick is every one of these items, I figure out where it is in the next array, and that's almost good enough to solve the problem. One of the problems that can happen, however, is that in the next array, you may have a situation where two things that are adjacent in this array, their logical location in the next array is way far apart. Like suppose, there's no restriction that says, so I got a situation here where everything in the next array is between 3 and 8, although I need more low order bits to distinguish floating point numbers or something, because 3 and 8 is not enough different values between them. There's no rule that says that things in the next array have to be uniformly distributed relative to the things in this array. So one of the things that I do is I go and I stick in every 10th item, say, and I put them in this array and put forward pointers there. And that lets me avoid the worst case situation of having to do, having things far apart. So you put ghost entries. The thing is, I haven't shown you how to do the insertion, so it's, but basically when I was building this thing, I could have sampled this array every 10th item and also merged those values in here. Does that make any sense to anybody?
Oh, it does.
But in that case, you are actually adding more values than you're inserting, because you're adding ghostings, and then you have to maintain those properties.
That's true. You're adding more values, and if we have time, I'll show you the analysis. But the analysis works out that it's less than, that it doesn't affect things. Because basically, if this array is half the size of this array, and then I throw in 1 in 10 items on the next array, so I've made this array 20% larger, it's still a geometrically increasing set of arrays. So that basically doesn't affect the analysis.
Well, you can't grow it, so you've got to grow it.
Well, let's talk about how to do insertions, right?
Sure, okay.
Because it'll be easier to talk about this stuff. Erase some of the stuff that's noise.
The key word I'm looking for is balancing, I think.
Yeah. So, but to talk about balancing, we have to have an algorithm for insertion.
Sure.
And that's going to satisfy these properties. So I'm going to start with an empty array. I'll do insertions by example. 4 items in that array, 8 items in that array, and 2 in that. And so the first, so I get to pick numbers now. So I'm going to insert, a 12, and I have an empty data structure, so I can only put it in one place. So nothing interesting there, because I was completely constrained. And now I'm going to pick a number.
17.
17, okay. So I'm going to put a little temporary array here to say, well, if only this array weren't full, but I'm going to make a little temporary array. If I have a 12 and a 17, I have to merge them together. I put the 12 here and the 17 here, and I erase these two guys. And really, I had no choice for this one either. I had to put both items into the second element, and this second element has to be sorted, so I didn't have any choice. Now, I actually have a choice. Pick another number.
13 and 14.
Just one.
Oh, yeah. I'm picking up a sequence because.
Okay. 13. And I could have put the 13 down here and the 12 up here, or the 13 here and the 17 here. I had some choice, right? But the simplest thing to do is just to put the 13 in the first empty spot and be happy with it. So essentially, every other time I do this, I'm going to be facing an empty spot, and every other insertion just gets to put the value there, right? So now, you wanted 14, right?
Yeah.
Okay. So 14, well, I'm going to have to do a merge, so I'm going to have a little temporary array over here. 13 and 14 are merged together, so I'll empty that. And now I'm going to merge these data structures. I don't, 12, 13, 14, 17. And I didn't have any choice as to where things end up here because I have 4 items, they have to go in this array, they all have to be sorted. So I've just given you the algorithm that I follow to do it. So now let's pick some more numbers and insert them. And 5, okay, so 5,
99.
9, so
99.
9 here, so that gives me a 5 and a 9, and I erase those.
3,721.
Let's do small.
Okay.
Let's do smaller numbers so that I don't.
100.
100. 99. And then 98. So then I merge the 99 and the 98. And I get that, and then I merge those two, so I get a 5, 9, 98, 99. And I merge these, and I get a 5, 9, 12, 13, 14, 17, 98, 99. I haven't done a very good job of aligning. I erase that. So you can sort of see that once in a while, I have a really expensive insert.
So if you have a trillion items.
Yeah, if I have a trillion items in there and they're all packed in, then one item causes me to merge the entire disk full of data, right? So one of the shortcomings of this first version I'm going to show you is that this data structure has good amortized behavior, but bad worst case behavior. On average, it behaves well because it's going to take a long time before I insert that trillion items. And so that if I sort of charge that trillion item merge against all the previous trillion insertions, it doesn't cost very much on average. I'll show you how to de-amortize it, but you can only sort of do one step at a time. So, okay, we've basically got an insertion algorithm now. You insert something, you sort of follow this carry chain. If I think of writing the number in binary and I've just incremented it, the length of the carry chain tells me how many merges I'm going to have to do. Right? So, let's do a little analysis of this and then let's try to fix up the deficiencies of the data structure. The deficiencies of this data structure include this amortized issue that the items, once in a while it's really slow. It also has another problem, which is that the items are fixed size, and real databases like to have variable sized items that you're putting into them. And I'm not going to really talk about how to do that. What else is the problem? I think, and there's the search cost time, which I haven't really completely finished talking about. Okay, so I'm going to erase some stuff here and do a little analysis of what an insertion costs. So what does an insertion cost? Well, an insertion costs, what we're counting here is disk IOs. So we've got to count up the number of disk IOs. Every time I insert an object, that object could end up being placed here, and then later it gets placed here, and then later it gets placed here, and then later it gets placed here. So it's It's sort of the number of moves. So the insertion cost, in the worst case, is the number of moves times the cost per move. The number of moves is log n, because there's only log n arrays that something can go into. Right? So that part can bound the cost. And that log n is going to be this log n. And now I have to figure out, well, what's the cost of doing a move? We've got these two, we're doing a merge. We've got two big arrays and merging them together. What's the cost of merging an array of size n and another array of size n into an array of size 2n?
And sorting the elements at the same time,
Well, remember, it's a merge, right? These are already sorted,
but not in relationship to each other.
but they are sorted individually. So it's not a full
Right.
sort, it's only a merge,
Okay.
right? So how do I do a merge? I put one finger here and one finger here, and I take the minimum and I put it down there. And then I take,
2n.
so it takes 2n to read all those blocks,
Right.
plus 2n to write all those blocks,
Or
right?
one end, depending on your.
Well, so the total number of objects that I've read or written is 4n, right? That's the number, except that each time I did that, it's really 4n over b,
Right. So read block.
because I don't actually have to do a disk I/O except one every b items, right? And then there's an additional reduction that happens of how many, I did all this work, which that's the cost of the merge, 4n over b.
But isn't the B different for each block?
No, there's no block size here. The block size is whatever rate, whatever transfer size is happening in the underlying disk subsystem. So if I have a giant terabyte array, I don't think of having a terabyte size block. I read a megabyte at a time into my buffer. I read a megabyte of this, or read a megabyte of this. I do a merge, and when I fill up this megabyte, I eject it and read, and keep going. So think of doing this as I'm doing this merge operation, and the primitive I have is I can do reads and writes of 1 megabyte at a time. The number of reads and writes I have to do is the data size divided by a megabyte times 4, because I have to read it and write it and write it. But the total number of elements that I've moved, this is kind of funny because this is the cost per move of merging a whole bunch of things. This promoted not one thing, this promoted 2n things from here to here. So I have to divide, this is the cost per move, I have to divide by 2n, because I didn't just move one item from here to here and pay this huge cost. I moved all of these items from here to here, and this, I'm trying to figure out the total cost of moving, of all the insertions that I've done. So these n's cancel, can ignore the constants, and that gives me big O of log n over b. Does that make sense?
Of 1 over b.
Log n, because there were log n, I'm doing this whole
Okay.
calculation. The number, so each item had to move log n times, and then each time we moved an item, it got carried along with log n, with b other items. So the cost of moving it was like 1 over b, because the moving van came up, you loaded a whole bunch of stuff in, the cost per book, the number of moving van trips per book that you're moving is really small, right? Amazon doesn't go and every time somebody orders a book, drive a truck out to your house and give you the book, right? They have a big truck, they load all the books in, they take it somewhere, and they take it to this stage, then they divide it into 2 groups, and then they finally end up delivering your book. But they're not moving a whole bunch of trucks all the way across the country every time you buy a book. And they're taking advantage of the fact that the cost per book, even though it's a big expensive truck, the cost per book of driving a truck 100 miles full of books is really low. Okay? So that gets me this number. And now how can let me go ahead and give you the hint of how to de-amortize it. It's not hard. I want to make it so that the average case is like, the worst case is like the average case. And it turns out that what if when I were going to merge these two things, if I just left this around, so I've got, I had 12 and 13 and 14 and 17 and 5 and 9 and 98 and 99. And if I were to put a little star on here that says this one isn't ready, and what I could do is every time I do an insertion, I could do one operation of moving the next item from up there to here. So I have a little pointer to here and a little pointer to here. So I move the 5 and bump that cursor. And every time I do some work up here, I do 1 unit of work down here. And then I do another insertion, and I do another one. It turns out that schedule will cause this data structure to fill in just in time before you need to have this array free. And so then, or you could just have a background.
And what's the cost?
In the meanwhile, while this
Those
thing is
pointers.
still,
Sorry, what's the cost of following all those pointers while it's being filled?
well, we can assume that we have a megabyte buffer here and a megabyte buffer here and a megabyte buffer here. There's only log n of those buffers around, so we just assume that we have enough buffering for all of those. There is a requirement that the memory size be at least the memory size better be at least big omega of b log n.
Okay.
So if
Block times log n. So
what?
block size times.
the block size times the number of depths of this tree.
Okay.
So if the
Got it.
block size is a megabyte and log n is 40, because I have 1 trillion items,
Yeah.
then it turns out that the first several blocks is a little bit of hackery at the very beginning. I don't need a full megabyte for this one element thing, but ignore that. We're doing an upper bound argument, so if we say let's assume a megabyte. So I need 40 megabytes for the buffers for this, in that case, for the trillion element data structure, which is really like 100 trillion bytes, because we assumed 100 bytes per item. So it's a really big data structure, and I need to have some buffers here and there. And really, I don't, maybe I need 3 log n, and maybe it's the constant hidden inside the big omega. Maybe it's 3 b log n or something, but it's not something that's out of control. So that's how you de-amortize it, is basically and meanwhile, while this thing's being filled in and isn't ready to go yet, you just keep doing your lookups. Do a lookup here and a lookup there separately. And it only costs a factor of 2, because factor of 2, as I put on my theory hat, I say, we can ignore a factor of 2, it's just a constant. And then it turns out, you try to build one of these things and you put on your engineering hat, you squeeze all the factors out that you can squeeze out, right? You don't just leave factors of 2 lying around if you can avoid it. So as an engineer, why do this thing of carefully scheduling? Every time I do an insert, I'll move one item. I might as well just stick a thread on here and have it do the merge as fast as it can. Right? And as long as this thread is doing merges faster than these insertions arrive, it'll stay ahead. So I might as well just get it over with, right? But the rule is I have to be able to keep up at least with. I have to do 1 unit of this work for every unit of insertions. So that's a pretty weak bound, because this is all happening inside the storage engine, whereas that's involving the whole MySQL stack. To do an insertion is much more expensive.
On the other hand, it's like just writing to an empty space doesn't cost you much in terms of like hardware execution. Whereas like reading that block, you might just have way better performance if you read in large chunks to do your merges.
Yeah.
Yeah. So this is why we read in megabyte size pieces
okay.
rather than even 4K is too small. The choice of how big your data block should be when you actually do disk I/O is, well, if I assume that when I'm doing a block I/O that I don't have any control of where the file system or the OS or the disk, if it's, has actually put the block, then there's 2 components of the disk access, right? You have to move the disk head, which is maybe 10 milliseconds, 5 10 milliseconds, depending on what kind of disk you buy, or SSD, it's much faster. You actually have to transfer the bytes. And what you'd like is that you're getting within a factor of 2. This is being a theorist again. So the strategy we follow is we want to get within a factor of 2 on the disk bandwidth. We want to make sure that we're using half the disk bandwidth. So what we do is we choose the block size. As the block size is too small, then you spend 10 milliseconds moving and then no time fetching bytes. If the block size gets to be a gigabyte, well, I tend to spend 10 milliseconds moving and then 10 seconds reading the bits. And it may be that I am not getting within a factor of 2 in that case, because what if I really only needed 1 bit out of that 10 gigabytes, right? If I only need to if I'm doing a lookup and I only care about one particular value and I knew where it was, I want to read a small block. right? So in that case, I'm seek bound. So that if you choose a block size where the seek time equals the time it takes to move the block, then you're guaranteed to be within a factor of 2 of the optimal thing that you could have done if God had come to you and said, you know, I know what the disk IOs are going to be. You should make the block size be this big. And you know, if God had done that for you, then he would be maybe twice as fast as what this strategy would give you. So you say, okay, I'm willing to be within a factor of 2 of omniscient, which is, you know, it's a start anyway. Okay, so what's the last thing? Did the cascade? Okay, did the sort of. So now how much time do we have left? Are we out of time or?
Negative 3 minutes.
Negative 3 minutes. Okay.
That's okay.
So I can stop then, so that the next people can go.
Well, there's a 15-minute break.
Oh, there's a
so if you
15-minute
want to
break.
like just take a few minutes, wrap up, and get questions.
Okay, so returning to the question of how do I build those ghost pointers that I wanted in order to get the search costs down. Essentially, what you can do is, there's this observation that I've done all this work to build this data structure. And while I'm doing that, there's this next data structure that I want to, while I'm filling in this thing, I want to fill in every 10th item of this thing into this one. So I want to take the 5 and the 9 and the 98 and the 9 and the 12 and the 13 and the 14 and the 17 and the 98 and the 99. And down here I say I have items like 100, 101, 102, and so forth. And so what I can do is, while I'm at it, I can merge in every 10th item. So I go ahead and put the 101 and the 102 out here. And because this size is only twice as big as this one, the cost of merging these 3 items together, this size of n, this size 2n, this size 4n, the cost of merging all of that together is 8n, which is big O of n, right? So it doesn't change the big O's. And so I can do a 3-way merge and build the ghost pointers while I was doing it. And the reason why that works in some sense is this data structure is not changing, right?
Okay.
And it won't change until there's a big cascade that comes along that causes an overflow, and then I don't actually change it, I make a new one. So this data structure is a nice constant data structure, so I can basically take all the time in the world I want to build the data structure I want to index into this thing, so that I've got all the forward pointers down to the next layer of the data structure. And while I'm at it, I might as well actually build myself a B-ary index for this thing. Build another little array here, which is every bth item. And then build another little data structure here, which is every bth item of that. And that'll give me log base B of n instead of log base 2 of n for the lookup cost inside that array. And so there's, basically I can build all that stuff and hide that all in the cost, because basically the cost of building this data structure was big O of n over b, and that's so much time that I can build any interesting data structure I want inside there. Okay, so I hope that this has removed some of the mystery behind how you can get simultaneous good insertion performance and good lookup performance out of a data structure. It's a, the way I phrase it, it's a data structures problem, and then what Tokotak's doing is they built one of these and we're trying to sell it. So, any questions?
So the say range reads means that you have like really fat pointers that give you like positions in each of the buckets, each of the arrays.
For doing.
I mean, if you want to do a scan on the.
Oh, you want to do a range query.
Yeah, so if you do a range
So a range query, you just
cursor?
position one cursor.
Yeah.
A cursor comprises log n cursors.
Yeah,
and
yeah,
log
exactly.
n, or
Okay.
you have to compare the top log n things, and then emit the next one, and then you bump that cursor. So yeah. And one of the things that happens is if you know all sorts of engineering tricks you can do. Hey, if I'm doing a range query across this and this, why don't, even if I don't have this other one ready to go, why not go ahead and merge those together into the bigger one now? I've got the disk head positioned properly.
If it's not ready, you don't know if there'll be an element in between.
Well, the invariants start breaking up, because instead of the arrays being a factors of 2, there's some other rules going on. But it's always legal if I weaken some of those constraints that I wrote up at the beginning about that there's exactly arrays that are size 1 and 2 and 4 and 8, and says, well, why not have an array of size 12? All the data, the algorithms work.
And you
I
can
could
add
take
it
any two of these and merge them
right?
together into a bigger one at any time.
Yeah, but
We can get out of
but
it.
that means that just a little bit,
Yeah, yeah.
you need to move a lot just for doing one search.
Yeah, we
If
always want to get
if
to
you
the
are
So did
Well, you never have to